Hello everyone. My name is Reem Dakhli from Tunis Al Manar University, and I am a second year PhD student in computer science. It is my honor to be part of this remarkable conference, and with great passion, I stand before you today to present my paper entitled Exploring Explainable AI Attention Maps to investigate the effects of distance metric and lesion-shaped border expansion size for effective content-based dermatological lesion retrieval. In simpler words, we thoroughly investigate in studying the impact of different lesion border expansion sizes along with different distance metrics in the efficacy of a retrieval system. And these variations will be explained using attention maps. Over the course of this presentation, I will delve into a brief exploration with our research, focusing on the importance of the selection of the appropriate similarity measure for an effective content-based skin lesion retrieval in the first place, and I will shed a light on the improvement that could bring the skin lesion border to the significance of the extracted features. Additionally, to the explainable techniques opted in this study to increase trustworthiness. Following this, I will represent our proposed method that aims to address the aforementioned challenges along with the findings of our experimental results, offering insights into the potential of our approach. Moving forward, skin cancer undoubtedly stands as one of the most alarming types of cancer. Acknowledging this reality, numerous automated diagnosis systems have been proposed. In addition to the invaluable assistance provided by these classification systems, which have already proven their worth in aiding dermatologists, it is challenging for dermatologists to understand the underlying reasoning behind their predictions. In contrast, content-based skin lesion retrieval systems offer visual explanations by retrieving similar cases with comparable features, which mirrors medical procedure. Attention maps here come as an endorsement to visualize the considerate feature patterns in the classification phase. So, to achieve an accurate diagnosis and retrieval system, two major challenges lie ahead: feature extraction and similarity measure selection. Similarity metrics are of major importance in retrieval systems, and each similarity measure leads to distant performance depending on the feature vector. On the other hand, despite the capabilities of deep learning layers to extract features from raw images, many researchers have demonstrated that the quality of extracted features can be enhanced through segmentation. This is primarily due to the ability of segmentation to eliminate irrelevant regions. In the specific context of skin lesion image retrieval, several studies explored the significance of the surrounded border lesion. However, the size of expansion is still challenging to decide. Deep learning models achieved impressive accuracies in deep learning skin lesion diagnosis, but their black box nature can be challenging. By black box, we mean that it can be difficult to understand exactly how these models arrive at their conclusions, even though they are very good at identifying patterns. Dermatologists need to trust the system's recommendation, so they rely on the understanding of the why behind the diagnosis. But a black box model makes it difficult to confirm the model's reasoning. There are methods being developed to make deep learning models more interpretable, known as explainable artificial intelligence techniques. The mostly used of these XAI techniques are heat maps, which can help to visualize what parts of the image influence the models the most. In our study, we opted to the method of expansion pixel by pixel on the lesion or on the lesion border as presented in the left figures, noting that morphological operators transforms the irregular edges into lines or into linear shapes on the right figure, which makes the border shape noisy. However, dermatology experts have confirmed the importance of the expansion of lesion borders while maintaining the same lesion shape. Hence, In the proposed method, it consists of two main phases. Firstly, in the offline feature extraction phase, segmented and expanded skin lesion dataset are trained using a deep learning architecture, resulting in both classification model and feature vector datasets. Secondly, the offline testing phase consists of processing the query image identically to the offline phase, resulting the feature vector of the query image. And lastly, the system classifies the query image to the appropriate class and retrieves 10 similar cases after comparing similarities. Building upon the robust foundation of the Inception Resonate v2 architecture, our study advances with a focus on practical implementation, recognized as one of the foremost models in contemporary deep learning. Furthermore, we augment this architecture with a soft attention layer strategically appended to the final fully connected layer. This addition enhances focus on the pivotal features, refining model performance and efficiency. Transitioning to dataset considerations, our exploration delves into the HAM dataset, renowned as one of the largest datasets yet challenged by class imbalances. In response, we employ a suite of data augmentation techniques, including random flips, translations, and rotations. These interventions are pivotal in mitigating overfitting risks. So we selected Cosine, Bray-Curtis, and city block distance measures based on the results these metrics show in the current state of the art, and their formulas are as follow. Now, the obtained results show with a broad outlook that both classification and retrieval results depend clearly on the variation of expansion values. In fact, classification performs the best, particularly when expansion value S is equal to 6 and 7, while when expansion size S is 0, which means traditional segmentation without expansion, shows minor results, which confirms the importance of the surrounding lesion border. Additionally, the precision at 10 retrieved images has the highest performance when expansion size is equal to 5, shown in the table on the right, with 59.6% of the 10 retrieved images were relevant, along with the Cosine distance metric that has best retrieval performance overall. Now, this figure represents a sample of the retrieved results by the proposed content-based skin lesion retrieval system on two query images of two classes. In the first sample query of the actinic keratosis class, the system proposed 9 pertinent similar images and one image that is visually similar, while belonging to basal cell class. Relying on the attention maps explanation, it is possible to interpret that misclassification is likely to occur in this case because lesion images may share the same features such as color or differential structure, but different in morphology or area affected by these features, however belonging to different lesion classes diagnostically. Likewise, for the dermatofibra query image, the misclassified case is explained due to the lesion size comparing to other lesions of the same class, which can falsify the distance metric. Overall, sample failure cases of classifications are shown associated with their attention maps in this figure. It is clear that most of the failure cases concerned lesions with smaller sizes relatively to the image size or to the other lesions of the same class, where the lesion of interest is misrepresented by the large region that should be disregarded or neglected. This can be explained by the fact that the large background region is overshadowing the region of interest. To conclude, the main objective of this study was to evaluate different approaches for retrieving similar skin lesions by comparing expansion sizes and distance metrics. We gained valuable insights into optimizing the retrieval process. We employed the Inception ResNet V2 model to classify and extract features from skin lesion images with various expansion sizes. Our findings suggest that the cosine metric, distance metric performs particularly well, especially with an expansion size of 5 pixels. This research paves the way for further explorations. So in the future, we aim to incorporating dynamic lesion size selection for even greater precision.